All right, welcome back. Still got people straggling in, but we've done a good job of staying on time, and we're going to continue to do that because these sessions are pretty spectacular, and I think you'll find them extremely interesting. So we now are going to turn over to two speakers. As I said before, you heard from Aerospike. We're done. You're going to now hear from speakers, other people. First, we're going to hear from Theresa Melvin from HPE, and then we're going to hear from Matt Cochran from the Trade Desk. And I want to first invite Theresa up on stage. Give her a big hand. Thank you so much for joining us. Theresa serves as the chief architect of AI-driven big data solution for HPE's open source profession and worldwide solutions group. Whew, I got through that. That's a big job. And I had the pleasure of having dinner with her last night, and she shared with me just a couple of the things she works on, which are mind-boggling. So I'm going to get out of the way and let you hear from Theresa directly. Thank you, Theresa.
Thank you very much. Thank you. Well, I want to welcome everyone, first of all. And what we're going to talk about in this session is interesting. But what's going to follow is in practice. And I say that because last month, I was at Flink Forward with the Trade Desk again, Jonathan, and you're gonna find that at the scale that I develop for, we pretty much all run the same thing, because there's nothing else out there that can do what we need to do. And I want to wrap with enough time to do questions. So as I go through this, I want you to think about questions. Think about how what you're going to see could eventually apply to your organization, how you use some of the technology and tools, and the things that are out there that you don't know a lot about that you would like to know more about. Ultimately, I'm a developer, and I run the Open Source Solutions R&D Lab out of Fort Collins, Colorado. And the bulk of what we do there is open source development. We are given really strict requirements from Hyperscale and Extreme-Scale accounts. And then I go out and I find the whatever it is that's going to finish the equation that they give me. So I hope you enjoy a lot of the technology that you're going to see. So first and foremost, this is the goal if everybody comes to me. They need to go about an average of 60% faster. And they need to do it with 80 to 85% less hardware. And that's because they are completely maxed out. They are pushing 500 petabytes min. And a lot of them are moving to 1 exabyte and beyond within the next 2 to 3 years. The only way those financials work is you have to distribute everything. We are talking a 100% fabric-based design. So this means you are putting your databases, things that you would never put into a container and attempt to move around. You have those running not just out at the edge, but in the actual device. So think of a radio telescope, think of a car. You are putting full-fledged end-to-end stacks everywhere, from the device to the edge to the car to the cloud. The developer builds exactly what he or she is going to roll out throughout the entire infrastructure. We start at the bottom. We build on-prem, we build for cloud. Everything has to roll. Everything has to be seamlessly scalable. So I click a button and it goes wherever it needs to go. You can do that using an array of tools. HPE has Blue Data. That's definitely an option. For people who aren't using Docker containers, they use RKT with Kubernetes. You can leverage kubeflow tools throughout the entire infrastructure. The bulk of what I develop for is open source. I bring in commercial products like Aerospike when I can't find anything in the open source portfolio that can meet the SLAs that I have got to have for these pipelines. And a good example of this is automotive. So autonomous automobiles, I do a lot of development for the industry. And in 2016, automotive came to all the big vendors, all the big manufacturers, and they said, we have a data problem. We expect to have over 200 exabytes of vehicle data that has to be processed in more or less real time. And we expect this problem to occur no later than 2023. And we're looking to all of you to help solve this problem. We don't know the right tools. We know the tools to do it technically don't exist today. But we want to know what the best tools today are that will allow us to seamlessly move to the technology of tomorrow. And so that was our directive. And that has been where I've been stuck for about 20 months, is the real-time persist here. The real-time persist here is incredibly critical to this work because it is a system of record. It grows and it grows and it grows. And when you think about automotive, you are talking about 200 exabytes of potential growth across a global infrastructure. So some automobile manufacturers may try and keep everything. So they could have hundreds of exabytes of data potentially. Others are much more realistic in what they are going to try and collect. So they may only try to process exabytes of data and store hundreds of petabytes of data. Either way, this real-time persist here, this NoSQL database infrastructure, it's beyond critical. And so that's where we are going to talk about the world of big data. So this is where the problem begins, data. Okay, we know we can store it. Object storage, it definitely solves the big data problem. So we have Hadoop. We have Hadoop with erasure-coded storage. We have object storage. We have S3, which is basically object storage. Azure has blob storage. You name it. Everybody's got some type of object out there that meets the deep scale of big data. However, the problem with big data is it's really, really slow. All you do is add more and more and more. And no matter how smart your developers are, you're still collecting more data. So no matter how much planning and coalescence you build into your big data framework, it still takes a lot of time to pull all this data out. You're basically doing nonstop batch processing. So we have to get a little bit smarter when we move into hyperscale. We have to distribute everything. Everything becomes a solution-based design model, which means we plan for a full end-to-end architecture. It's got to be modular. The code has to be completely portable. What does that mean? It means actually something quite different when you're dealing with hyperscale. That means that whatever my web team, my front-end design team, the guys who build in Java, I need their stuff to actually work on my GPU systems, which are Python, and vice versa. I actually have to be able to develop models that can run on my Java big data frameworks. You have to have that much foresight to be able to build implementations that can run anywhere. This is very hard. These are different skill sets. We have the front-end web developers. Again, these are typically Java, PHP, JavaScript. And then we have machine learning, deep learning. Those are Python. Those are our guys. And then we've got the HPC guys, the guys who really, really want to get down and dirty and talk about nanoseconds. Those are our C programmers. Pretty much everybody in the room, I think, is a C programmer. So those are the people who really care about performance, who care about speed. Everybody speaks their own language, and it's really, really rare to encounter a skill set that can cross that divide. So you look for tools out there that can do it for you, tools like Apache Beam, which is open source. And so we do a lot of work around Apache Beam, especially when we build for the Extreme-Scale, which is also synonymous with the Exascale market. We have to have completely modular, adaptable, and very, very flexible, fluid designs. They have to be really fast. But fast is only relevant if you are going in the right direction. So you have to have a plan. Your plan has to be well thought out. It has to be very well designed. And you have to know what you're architecting for. When you think about exascale accounts like automotive, like astronomy, and aerospace, and for instance, the new jet engines that are coming out here by Rolls-Royce and Boeing, an 8-hour flight. they have the potential to generate a zettabyte of data that starts with a Z. That's a lot of zeros. They have no idea what they are going to do if they attempt to collect all the data from these 5,000 sensors per engine. So you have to have an extreme level of planning at the get-go. Are we planning for terabytes of data of ingest per second? What is the payload? Is it actually 1 terabyte of ingest per second? Are we talking about 1,100,000,000 byte events per second? All of this matters because it actually matters what database you would put in front of solutions like that, what real-time streams tier you would put in front of that. We also have accounts at Extreme-Scale that are actually trying to retain a very small amount of data, but they have very high velocity and very deep ingest. So a great example of this is the square kilometer array. Even SETI, anything in astronomy, they have piles of data, piles of data. They are talking about bringing in potentially an exabyte of data per day. They need to be able to scan all this data and only retain, they figure, about 1.5 petabytes of data per day. That's tremendous processing. That requires a level of scale that delves all the way down into exaflop processing, which doesn't even exist today. The brightest people in academia, government, and industry are currently working on that problem right now. So the question is, who is actually attempting exascale? And it's a great question. I get asked that all the time because people think that it is very much sci-fi. It's actually not. I mean, think of the Facebooks, think of Google, the US government, the NSA. These are all 10 exabyte plus footprints. Look at how they do it. They're fully distributed mesh frameworks. Academia has already got exabytes of data that they have no idea how to manage, how to do deep learning on. They are looking to partner with companies who know how to move this type of data around, how to store it, how to ingest it, how to make it more useful and flexible and productive to the entire world, not just them. So we also have manufacturing, we have insurance, finance, healthcare, you name it. All these industries have all the sensor data. Everybody's trying to collect more and more and more. And nobody really has a plan, a good plan in place on what exactly they're going to do with it. So these are the types of problems that we all work to solve with these designs. The most important question is cost. They have to be able to afford these solutions. You can build the best design in the world with the best algorithms. You can do in-flight stream analysis and deep learning, but if they can't afford it, what's the point? So it has to be layered. They have to be able to implement the design in stages such that it fits into their entire budget. And we already know that hardware is a considerable cost of any hyperscale implementation. They're going to spend somewhere between 60 and 68% of the budget on hardware. That doesn't leave a lot for software. And this is why the work that I do is so heavily focused on open source. There's a tremendous amount of great open source tools out there that will meet the greater needs for a lot of these organizations. So it helps them figure out where they're going to spend their software dollars. And they're definitely going to spend it on that real-time persist tier. So as I was saying, there's one stack. This one stack, the developers build on their high-end laptops, and it's deployed everywhere. It's deployed out at the edge. It's deployed on the edgeline servers, where additional maybe schema application or any other coalescing is done before data is sent to the core and cloud. One stack to meet as many problems as can be solved for that particular use case. We minimize the number of tools that are required for the actual implementation and support of the project. Collaboration on this, it requires in our situation, it requires HPE, the customer, and partners. These are too big. It's too big for one company to do. You have to have really, really rock-solid partners in there. And this goes back to Apache Flink. So I work a lot with Apache Flink. It's really fast. It does things no other streams processor does. And likewise, I sought out Aerospike, and you're going to see why here in a little bit. And basically, you take the best of the products that you find out there, and you do a lot of development to merge them where it makes sense for customers that it makes sense for. So when you think about Apache Flink, it currently runs an embedded ROCs DB database. Well, at Hyperscale, ROCs doesn't scale that great once you hit double-digit figures. So Aerospike scales wonderfully. And so that's something that I've started working with the Apache Flink committers on for the clients that I designed for, is a custom Aerospike backend for Apache Flink to solve the scale and the HA issues that they currently have. So these devices, they can be anything. It can be anything from a tractor. So more and more in agriculture, we are dealing with not just connected, but autonomous. So self-driving tractors is a new thing. Pretty soon, we're going to have self-driving semis out on the road. Walmart's entire fleet is going to be autonomous one of these days. So all of this requires special hardware that has to sit inside these vehicles to be able to perform analytical processing as close to that data as possible. You cannot ship this data to core. It takes too long. You have about 30 milliseconds for a reaction to occur. If you send that data to core and back again for processing, it's going to take, at best, right now, about 80 milliseconds, which means you have moved 4 feet. Your front end is sitting in somebody's back seat by that point. So we need better technology, we need better code, and ultimately, we have to move the compute to where the data is. And in the case of autonomous vehicles, that's the car. We're basically moving server technology into the vehicles. Edge, there's always going to be an edge. So even if you move compute to the vehicles, you have to look at how much space you have to work with there. You don't have a lot of space. So you're going to do as much as you can. You're going to do your real-time predictions, your analytics, and then anything else that has to go to core and cloud for additional processing, you're going to send it to the edge because it's tiny. Typically, these payloads are, let's say, 30 bytes in size. So you need to coalesce that data into as big a packets as it makes sense to send. Everything you send to core costs you time and money. So everything is calculated. You do absolute math everywhere. At every end of this implementation and design, you are running financial analysis just to make sure, does it make sense to send this data on? How much are we going to save if we process it in place? And what is it going to cost us in the long run if we don't do anything with it and just discard it? So it's a bit of a guessing game nonstop. So tools right now like Mosquito are very, very popular. However, these are not going to fly at extreme scale because we have the additional layer of a broker. You have to move to a decentralized design. So something like DDS and OpenDDS, which is completely decentralized, and it doesn't require that middle layer of a broker in there. Network fabrics. This is really, really complicated technology that I am not qualified to talk on, but this is ultimately what has to happen at extreme scale. You basically spread your networking between core, cloud, everywhere, multiple data centers. Facebook is the one who basically created this for open source, and HPE also has its own platform called Plexi, which does the same thing as a commercial product. So you'll see that everything that I develop, there is an open source path for, and there's a commercial path for, so that a customer, they have the option. Do they have the skill set in-house to basically roll their own and support it? or can they afford a commercial distribution? And that's really what I love about Aerospike. Aerospike has that community product, which I've actually been using for years, quite successfully. I've never needed to reach out and get enterprise. It performs incredible. And I've not had a use case that I've needed to actually use enterprise for. It was just really rock solid. It was bundled around a Docker container. I could move it anywhere I needed to move it. And it just worked. It never failed. It never went down. And it scaled better than any other key value store that I was working with. So that ultimately became kind of the back end for the bulk of my fronting designs. Apache Flink at this level of scale very much was always used simply because of its ability to do windowing. So I could go back, I could replay. I never lost data. I was able to do exactly once processing. It was very, very effective. However, when you're dealing with layers, you have to keep each tier in perspective. So that real-time processing tier, that's just one element of the equation. Ultimately, I have to be able to do lightning-fast predictions. So all of my models that are running on that deep learning tier, either through tools like Weka.io and Alluxio, or through a product like Apache Ignite. And what these do is they give me single namespace. Single namespace is critical when you are dealing with an extreme scale design. Because the last thing you want is to have to go out and modify codes to pull from an HDFS file, then go out and pull from a S3A file if it's Hadoop, and then go out and get all your POSIX data, and then go out and get all your NFS data. You want one namespace. So for something like Weka.io, you simply call a file URI. For Alluxio, you call an Alluxio URI, and it just reads in all that data into your machine learning applications or whatever the application is that you're using. So all of this becomes really, really critical when you are dealing with strict time frames. So turning this data into an intelligent science, it's end-to-end. We've come full circle. So believe it or not, we are now back at the streams tier when you talk about this. And what you're looking at here is an astronomy use case. So what they do is they take a picture of a spiral galaxy. Well, now in number 2, we are converting that into something that a computer understands. Basically bits and bytes. It's a bunch of numbers. And what that is in number 3 is you add a color scheme to it, and it's a pattern. So now every time a computer sees number 1, it knows, okay, that is number 3. It's going to classify it properly. This needs to happen in real time. Real time in my world is anything typically around 6 milliseconds. So in order to classify galaxies for exabytes of data in real time, you have to have better machine learning algorithms, and you have to have faster technology all the way through the pipeline. I have to have data that can process as much as possible all the way out at the device. I have to coalesce. I have to apply schema. Anything that I have to do at the edge. At core, that's where all the big iron hardware sits. That's where we're doing a lot of the heavy lifting for the deep learning. And then that model gets exported to the streams tier. And that's where we do everything that you see here. We take the data, we turn it into intelligence. So now we're going to talk about why we're here. All the work that I've been doing for the past 2 months, and I don't even know that it's been much over 2 months. The HPE server team sent me 3 prototype servers, PMEM servers, that they were getting ready to launch, and they told me to just run some benchmarks around them. If I could do that, it would really help. And I was very anxious to do that because I've read a lot about PMEM. And the requirements that I deal with, these accounts ultimately need to be pushing about 10 million IOPS per second and that's 10 million IOPS per second, in order to have basically a financially sustainable footprint, which is about 100,000 instances. So, and that's physical pieces of hardware, most likely, sitting on a floor for their real-time persist here in order to manage about 100 exabytes of data, which would be automotive, that would be astronomy, that would definitely be aerospace. So any one of those high-end, high-velocity accounts, that's pretty much where they're at. The hardware today on the front end is all CPU-based. You can't move GPUs to the front end. That's a completely new code rewrite. That's a full code rewrite. CUDA code is not Java. You can't run Java on CUDA. So it doesn't make any sense to try and put GPUs on the front end unless you're going to be basically retraining your staff to write all your front-end applications. So the technology, the hardware on the front end has to get better, has to get faster. And I need really fast database. I need a really fast real-time persist here. So that is what we worked on. Intel's going to do an awesome presentation tomorrow on their PMEM DIMMs. The only thing you need to know for the work that I did is I worked only with the AppDirect integrations. So that means that I was able to recognize the PMEM hardware, and it leveraged either the FSDAX, which is a file system mount, or the DevDAX, which is a device. So it would either access the raw device or it would access the file system. And the implementations for all of these were different. So most of the implementations were either C or C++, and a couple of them were Java. There are some Python implementations out there. I've not tested any of those yet. I just saw that the bindings were available. So eventually, everything is going to have a path into PMEM. But for the test that I did, Cassandra was Java. Everything else was C and C++. And the prototype hardware was just ProLiant DL380s. And they had about 1.75 terabytes of total RAM, including the PMEM DIMMs. So for the PMEM, we allocated about 758 across 2 different mount points. So I had 2 PMEM mount points that were about 750 gig each, and that left about 192 gig for the operating system. These are also Cascade-Lake processors, which were prototypes. So you'll notice that I really don't have any model info for these processors. They're brand spanking new. So for DevDAX, that was Cassandra. These are all open source with the exception of Aerospike. So you can go out on GitHub, pull the implementations down, compile everything from source, and be on your way. It's not that easy. It sounds really easy. It's not. Cassandra, I had to work directly with Intel to get that to work. And there's just little nuances that you have to know. You have to run very specific kernels. Everything matters when it comes to that Cassandra PMEM implementation right now. And the thing is, you have to remember, with the exception of Aerospike, which I would call production grade, everybody else is in like a beta 1 format. These are not anything that are production ready. You need to do a lot of testing, and you gotta really get your hands dirty to get most of these to work. Aerospike took me all of 20 minutes to be implemented up and running. And it went so seamless and so fast that I thought I didn't have it working. And I reached out to the engineers and I said, I don't think this is working. And they're like, yeah, we have it built all the way in. It's in C, it's all the way down at the driver level. And I went into the logs, and sure enough, I mean, it was great. So in the benchmark that I did, I just did standard YCSB benchmarks. I didn't do any customization, nothing. I didn't give anybody any advantage. I took the raw tool, made no changes whatsoever, and I excluded Mongo, and I excluded Memcache. And that's because anybody who's using Memcached, they don't care about an SLA if they are persisting. So it really wasn't fair to have it in there. And Mongo is a document store. I don't think of Mongo as a key value store. So that, again, it didn't seem fair to put it in there. So those two are not in the test, all the others are. So it's a simple workload A, and which is a heavy update workload. So how YCSB works is you first load this data. So you are pushing, in my case, it was 500,000 records, nothing too crazy. I started everybody at 200 threads, and that's pretty much it. So record count was 500,000, 1 kilobyte standard file size, which I didn't alter. That's just what it comes with. It's vanilla. And 50% reads, 50% writes after you do that initial insert. So that is the core workload. How it actually went. Aerospike had no problems with 200 threads. No problems at all. The server did. So I had to throttle back the number of threads for Aerospike to keep the server from crashing, basically. So I moved it down to 1 thread per CPU. So I decided to just start everybody at 112 threads. And so that worked just fine. Aerospike completed all 500 million inserts in no problem at all. It then went, and that was about 200. I set the target, which is basically the throughput that you want it to do the updates and the reads at. I set that at 250,000, and I set the time frame to 4 hours. So either the job was going to complete, or it was going to be killed within 4 hours. And no issues at all with Aerospike. It completed in record time. ROX, I had to decrease all the way down to 10 threads. And then it was able to sustain a target throughput of about 80,000 IOPS per second. Cassandra, it killed it. It ran forever. So on the inserts, it did really quite well, 92,000 IOPS per second on inserts. But when I went to run the actual workload, which is 50% reads, 50% writes, the throughput just kept decreasing and decreasing and decreasing, and it just kept getting slower and slower. And after 4 hours, it just automatically killed the job. Same thing for Redis, only the performance was actually worse than for Cassandra. So it was going to take about 2.5 days for Redis to even complete the load on a 500 million records. So I gave Redis its own test, and it got 50 million records. And it was able to do that in 4 hours. So, I mean, when you look at the results, again, this is just vanilla, very, very vanilla. Yeah, Aerospike, they kind of speak for themselves. They were forced to do a throughput of 250,000. Had I not capped it, it would have exceeded 280,000. But I just decided to cap it on this particular run for 250. And the overall runtime, again, Aerospike ran this bench in about 30 minutes, about a half an hour. And the next closest one would have been ROX, which was just under 2 hours at 144. The throughput testing on this, it was incredible. So I did some more work with Aerospike just to see if I could break it, and I was disappointed. I mean, nothing. I threw 1 billion records at it, and the ops per second just continued to climb. I set that target throughput rate at 282,000. Did great, no issues, no hiccups, nothing, no out-of-memory errors, nothing. And then I went and I just wrote to a PMEM device. I just wanted to see what the throughput would look like if I just sent all data for a YCSB bench to one of these 750 gig mounts. What is that going to look like? So it started at about 485,000 operations per second. And the server became so I/O bound that it just started dropping and dropping and dropping. And then it eventually settled around 286,000 ops per second. And that was for a 250 million load. So I was impressed. Latency, almost non-existent on average. So pretty much, I think it was around 120 microseconds, if I remember correct. It doesn't even register on the charts. So it did really good. So as far as takeaways go, for PMEM, when it comes to is it worth the investment, it depends on the database. Now, all the databases out there, again, everybody's beta except for Aerospike. Everybody has a long road ahead of them. Aerospike sets the bar when it comes to the future. I can't do my work without Aerospike on a real-time persist tier and PMEM, with all the indexes in PMEM. I gotta have that warm restart. So when I have a customer which has tens of terabytes of per node, and they take it out to do maintenance, patch it, whatever. By having all those indexes in PMEM, the restart time was minutes with Aerospike. Now, when I did that exact same test with NVMe, it would take 45 minutes. They would have to rebuild all the indexes out of cold. So that alone is a very important value prop for the type of accounts that I develop for. And I think that's it. So thank you.